Hi, my name is Chike Abuah, and I'm going to be talking about DDUO, which is a system for dynamic analysis of differential privacy that can be embedded in general-purpose programming languages such as Python. This talk is going to be about data privacy and also about programming languages and how we can use programming languages as tools to both ensure that our algorithms are differentially private and also that they have a certain desirable privacy cost. Okay. One of the major design goals of DDUO is usability. We would like to enable programmers who are non-experts in differential privacy to write complex algorithms such as gradient descent in their favorite programming language and have the DDUO system automatically perform privacy analysis for such algorithms. As a proof of concept, we've prototyped DDUO in Python and we've done our best to express privacy concepts such as sequential composition naturally in Python with Pythonic idioms, such as with blocks. Alright, now let's get right into the mechanics of the DDUO analysis system. In DDUO, we use what we call data sources to track sensitivity and privacy information. Data sources are essentially wrappers around sensitive data that enable tracking of privacy information in the DDUO Python system. Each data source is associated with an identifying string, such as the name of the input file the data was read from. Here, the data source wrapper object is called a sensitive object. Sensitive objects represent sensitive information that cannot be viewed by the analyst. When a sensitive value is printed out, as we see on the right here, the analyst sees 1, the type of the value, which is a data frame in this case. 2, its sensitivity information, which is this dictionary or environment here. And 3, the distance metric associated with the sensitivity information, which in this case is the L infinity metric. The analyst is prevented from viewing the value itself. Now, sensitivity is key to differential privacy because it's directly proportional to the amount of noise that we must add to the output of a function to make it private. Recall that previously we defined sensitivity as the degree of change of function output relative to function input. DDUO tracks the sensitivity of a value to changes in the program inputs using a sensitivity environment, mapping input data source identifiers to sensitivities. Our example program here initially returns a sensitive value with the sensitivity environment mapping data.csv to 1, indicating that the underlying value is 1 sensitive in the data contained in data.csv. The DDUO system tracks and updates the sensitivity environments of sensitive objects as operations are applied to them. For example, adding a constant value, such as the number 5, to the elements of a data frame results in no change to the sensitivity environment. However, adding the data frame to itself doubles the sensitivity, because now the data frame influences the output twice as much. Finally, multiplying the data frame by a constant scales the sensitivity by that constant, and multiplying the data frame by itself results in infinite sensitivity. Alright, now I'm going to talk a bit about conditionals, because this will motivate the design choices for privacy analysis. Conditionals and other branching structures are challenging for any sensitivity analysis, but they present a particular challenge for our dynamic analysis. Consider the first conditional over here. Here the two branches have different sensitivities. The else branch is 10,000 times more sensitive in its data sources than the then branch. Static sensitivity analyses handle this situation by taking the maximum of the two branches' sensitivities, assuming the worst case, but this approach is not possible in our dynamic analysis. In addition, special care must be taken when a sensitive value appears in the guard position, as in our example. Static analyses typically scale the branch's sensitivity by the sensitivity of the guard. This approach results in infinite sensitivity for conditionals with a sensitive guard. To retain soundness in our dynamic analysis, DDUO requires that the conditional guards contain no sensitive values. A runtime error is thrown if DDUO finds a sensitive value in the guard position, as in our example. This approach does not limit the set of useful programs we can write, since conditionals with sensitive guards yield infinite sensitivities, even under a precise static analysis. Now, DDUO tracks privacy costs dynamically at runtime. Dynamic privacy tracking is challenging because the dynamic analysis has no visibility into code that is not executed. For example, consider the second conditional here. The executed branch of this conditional depends on the result of the first call to DDUO.Gauss. In other words, the privacy parameter for the second use of the Gaussian mechanism is chosen adaptively based on the results of the first use. Sequential composition theorems for differential privacy are typically stated in terms of fixed, non-adaptive privacy parameters, and do not apply if the privacy parameters are chosen adaptively. However, privacy filters and odometers were developed by Ryan Rogers and his co-authors in 2016, specifically to address the setting in which privacy parameters are selected adaptively. Alright, in differential privacy, the Laplace and Gauss mechanisms are typically used to introduce random noise, as we see here on the first line. Privacy odometers can be used to obtain a running upper bound on the total privacy cost at any point in the sequence of adaptive mechanisms, and to obtain an overall total at the end of the sequence. Privacy filters allow the analyst to place an upper bound on the desired privacy cost and halt the computation immediately if the bound is violated. So we can see an example of that here. DDUO's API allows the programmer to explicitly create privacy odometers and filters, as we see in these examples, and make them active for a specific part of the program using Python's with syntax. When an odometer is active, it records a running total of the privacy cost, and it can be queried to return this information to the programmer, as we see here where we print the Odo variable. When the filter is active, it tracks the privacy cost for individual mechanisms and halts the program if the filter's upper bound on privacy cost is violated. In addition to odometers and filters for sequential composition under epsilon delta differential privacy, DDUO provides odometers and filters for advanced composition and Renyi differential privacy. Okay. Iterative algorithms can be built in DDUO using Python's standard looping constructs, and DDUO's privacy odometers and filters take care of ensuring the correct form of composition. Parallel composition is also available via functional mapping. Advanced composition can be achieved via special advanced composition filters and odometers exposed in the DDUO API. For example, the simple loop seen first here runs the Laplace mechanism 20 times, and its total privacy cost is reflected by the odometer. To use advanced composition instead of sequential composition, we simply replace the odometer with a different one, seen second here. The DDUO library includes support for pure epsilon differential privacy, epsilon delta differential privacy, and Renyi differential privacy. Programs may use all three variants together, convert between them, and compose mechanisms from each. We demonstrate execution of a query while switch to the Renyi differential privacy variant using Pythonic with syntax blocks last here. For programs that make extensive use of composition, this approach yields significant improvements in privacy cost. For example, this program uses the Gaussian mechanism 200 times using Renyi differential privacy. For sequential composition, the total privacy cost is automatically converted into an epsilon delta differential privacy cost after the loop finishes. Alright, so now to wrap up the talk, I'd like to revisit gradient descent in DDUO. So one method of ensuring privacy in gradient descent involves adding noise to the gradient calculation, which is the only part of the process that is exposed to the private training data. In order to add noise to the gradient, it's convenient to bound its sensitivity via clipping to some L2 norm. In this example, clipping occurs in the gradient sum function before the result is passed to Rényi-Gauss-Vec to add the appropriate amount of noise. Now this table summarizes some of our results. These times are not fully optimized, but they are pretty good and pretty competitive, in my opinion. So we worked on gradient descent, like we've seen, the MWEM algorithm, private naive Bayes classification, and private logistic regression, using NumPy, Pandas, and diffpriv-lib. Alright, and with that I'd like to thank you for listening and thank all the contributors to this project.